So today we're going to look at some comparisons called ratios and proportions. And a lot of times these words are used interchangeably, but you need to make sure you understand what they are so that when you use them in your class, you use them correctly. But a ratio is just simply a comparison between two values. It can be written as a fraction, but maybe certain types of ratios are kind of confusing as fractions, so we're going to talk about that. Maybe talk about which ones should or shouldn't be written as fractions. So we have two main types of ratios. The first one is a part-to-part ratio. In other words, comparing a part of something to another part. Okay, so an example of that might be there are 2 girls for every 3 boys in a class. Okay, so when you have a part-to-part ratio, the best format is usually with a colon. So we would usually say that the best format would be 2 girls to 3 boys. Okay. And let's compare that with the second kind of ratio we can have, which is a part-to-whole ratio. So let's take the same maybe data, but let's talk about it differently. So I could say that 2 out of every 5 students in the class were boys or girls. Notice that if I add 2 and 3 together, I get 5, right? So that's where I came up with the 5. So in this way, we can write it as a semicolon again. Okay, so we could say 2 to 5 in this way. Okay, or we could represent it like this. Okay, the reason we don't really want to write a part-to-part ratio as a fraction is just because that's confusing if we've taught our students what fractions represent. Fractions are supposed to be a part on the top over a whole on the bottom, and so if you start writing part-to-part ratios as fractions, it really is confusing. So even though you might see them in fraction bar, if they're a part-to-part, it's really not great format. Okay, it can be really, really confusing to our students. All right, so if you haven't already, go ahead and print out the worksheets for the week that say worksheets to print, because I want to look at one of them right now. So it can be a little difficult sometimes to talk about what would be a ratio, a fraction, or both. Okay, so I want you to take out this worksheet. And let's talk about these. Maybe just pause the video and take a couple of minutes to take your guess on what you think 1 through 7 are, and then we'll talk about them. Okay, so pause the video and see what you think. Okay, so let's look at number 1. There are 9 women for every 2 men in class, so I might make myself a note that this is definitely a part-to-part comparison or ratio. So because it's a part-to-part, it's just a ratio. It would be inappropriate to list it as a fraction. It just is too confusing. Okay, so take a look at the wording change here. 2 out of every 5 students plan to be middle school teachers. So that is a part-to-whole, right? We're talking about the portion of you out of a whole group. Okay, so in that case, we really could write it as both. It is still a ratio. It is a part-to-whole ratio, but we could write it as a fraction, and that would kind of make sense. All right, number 3, brand A orange juice costs 7 cents per ounce, while brand B costs 6.5 cents per ounce. That's just a ratio. Okay, even though, again, you might see it in what looks like fraction form, it's not a true fraction. It's not even comparing the same kind of quantity, frankly. It's comparing money to volume. Number 4, 1/4 of the marbles in the jar are blue. Okay, that is both. Okay, that is a part-to-whole. You're saying 1/4 are blue, or one of the parts is blue out of the 4 total parts. Number 5, my average speed while driving to work this morning was 35 miles per hour. Okay, so you might see that written as kind of with a fraction bar, but that's really just a ratio. Okay, it's comparing distance to time, so not a part to whole comparison. Number 6, Jane drank 3/4 cup of milk. Notice this isn't even a comparison at all. This is just saying a measurement. That's a volume measurement of liquid. So that's just a fraction. Okay, so not all fractions actually are comparisons. Ratio means you're comparing one quantity to the other. You're not comparing 3 to 4, you're just saying it's a little less than a cup. Okay. And then last but not least, according to the Kool-Aid instructions, for each quart of water, you should add 1 scoop of Kool-Aid and 2 scoops of sugar. That is a part to part. You're comparing the part of the Kool-Aid that is water versus the part of the Kool-Aid, or sorry, the part of the Kool-Aid that is the mix, right, with the sugar. So this is just a plain old ratio. Okay. So the point of this little exercise is that we only really should think of part to whole ratios as true fractions. Okay, in other words, true fractions that we can do calculations on. Okay, so set that off to the side. All right, let's continue on with our notes. So sometimes we say that things are proportional. All that means, if something is proportional, is that the ratios reduce to the same common fraction. Okay, so for example, if you had a part to whole comparison that was 5 out of 10, that is proportional to 3 out of 6, okay, because they both would reduce to 1/2. Okay, so let's take a little break and look at this blocks looking worksheet. Okay, so this is going to show proportional pieces. All right, so let's first start with maybe the one that we know. Okay, notice that this has 4 blue, right? And we're comparing that to 6 green. So these are all going to be part-to-part comparisons. So although we're going to write them as a fraction, just know that it's not really true fraction form. So it's the part that's blue compared to the part that's green, 4 out of 6. Okay, so let's go back here. How could I then kind of compare it to what I have here, right? So notice I want to have 2 groups, right? So if I wanted to, I could group these in this way. I could say, okay, there's 2 groups of 2, right? Versus how many down here? There are 3 groups of 2. Okay, so if I want to compare those and make them what we would call proportional, I would need 3 groups down here in the green. Okay, so this would be a comparison for 2 out of 3. So let's try to do the same strategy. So again, this is always 2 groups. The blue is always 2 groups of some sort. And so how many groups would we need here? We would need 3 groups, right? So I'm going to draw like the group setting first. But then how many are in each group? How many blocks are in each group? 3, right? And all of these are green. Kind of sloppy, I know, but okay. So notice here we're comparing 6 to 9. Now let's look at this. If we grouped these into groups of 3, remember the green is always supposed to be groups of 3, then how many groups would I need up here? So I would need 2 groups, right? The blue is always 2 groups in this comparison. But notice within each group it looks like I have 5 blocks. And same here. So this is comparing 10 to 15. So just real quick before we do the last one, notice that all of these are equivalent. They are all what we would call proportional. All three of these reduce to 2/3. Okay, so maybe we don't really want to do a full picture here clearly, right? But let's stick with our same kind of strategy, right? We want 2 groups here versus 3 groups here. Okay, and then rather than drawing them, let's just write how many. So if there were 2 groups, there would be 25 blues in each, right? And then of course down here there'll be 25 greens in each. So it is still a comparison of 2 to 3. Okay, but then this one is going to be 50 compared to 75, right? 25 and 25 is 50, 3 25s is 75. So notice, proportional just means they all reduce to the same thing, right? Notice if you divided both of these by 25, you would get 2/3, and look how many is in a group. Notice if you divided both of these by 5, you would get 2/3, and notice how many is in a group. Okay, so that's by design. Okay, so we have some special ratios. There's a special ratio called a rate, and this is where you compare 2 different measurement types. So we had some on that sheet where I asked you to tell me whether it was a ratio, a fraction, or both. We're going to look back at that in a minute. But it's when you compare things that are either different measurements or maybe even different types altogether. So I'm going to give you an example. Like if you say miles per hour, sometimes you write the per as a fraction bar. Okay, you could always talk about miles per gallon. You could talk about a race and meters per second or something like that. So notice in all of these, this is distance over time, right? This is distance over volume. This is distance over time. So we're not comparing kind of like quantities together. You could have your students look on the gas pump, right, at how many dollars per gallon their mom is pumping in at Quick Check or something. Some others, maybe words per minute, if you're talking about typing speed. Beats per minute, if you're talking about heart rate. Okay, I'm just going to say etc. There are plenty of examples more than the ones that I just said. But notice all of these are comparisons of 2 different types of measurements. Okay. So if we take our ratio, fraction, or both worksheet out again, let's talk about which of these would actually be rates. Okay, notice this one is comparing money to volume, so this is a rate. Okay, and then this one is comparing distance to time, so this is a rate. Okay, this one's not really a rate, and it's because we're comparing the same thing, right? We're comparing volume in both cases. Okay, so 3 and 5 on this worksheet are special types of ratios called rates. All right, so in this class, we're going to discuss 2 main ways to solve a proportion, and I want you to know how to do both. Because drawing a picture like we did for that block exercise a bit ago is not always going to be practical. And we kind of saw that when we got to the last one where there were 50 blue, right? I don't want to draw 50 blue blocks. So we're going to use either a table or we're going to use a proportion with X for an unknown. Okay. A table is what you would probably use in the lower grade levels. You definitely wouldn't use true proportions until probably like junior high or so. But at any rate, you need to make sure that you can show your thought process and all that good stuff. All right, so let me demonstrate both methods. We're going to take kind of a simple example. All right, so let's say the ratio of boys to girls in a class is 11 to 6. And let's assume that this ratio is proportional to the ratio of boys to girls in the whole school. And let's say if there are 583 boys in the school, how many girls are expected? Okay, so let's start with a proportion because, to be perfectly honest, I think we're a little more comfortable with that. Let's say there are 11 boys to 6 girls. Okay, and that equals, notice, where should I put the 583? Well, the 583 describes boys, right? So I need to put that on top. So one way you can get away from maybe having to use algebra if you don't want to is you can just use a question mark, okay? So then I just want you to tell me kind of what happens here. Like, what do I multiply 11 by to give me 583? And clearly we would want a calculator for this, right? But if you use your calculator, you're going to see that it's times 53. Okay, so that means to make this proportional, I also need to multiply this times 53. Okay, so in the end, I end up having 6 times 53, or if you work that out, 318 girls. Okay. Another way, though, is just a table, and honestly, it's no different from what we just did. It's just that the table is kind of visual and organizational. So you could come up with a table comparing boys to girls. And we know there are 11 boys for every 6 girls. And then we know that there are 583 boys in the whole school. So again, you would just be looking for what the pattern here is. So if we multiply by 53 here, then we also need to multiply by 53 here. Okay. And notice in the end, you're doing the same calculation, right? So the table's not magical, it's just organizational. Some people that are more visual learners like a table. Okay, it looks neater, clearer, all that good stuff. Okay, so let's look at another example. So this time I just want you to use a table for the following. So let's say that I tell you that flowers cost $11 per dozen. And then I want you to use a table to find A, the cost of 3 dozen flowers. B, the cost of 60 flowers. And then C, the number of flowers you would get if you spent $77. All right, so it's important when you're making your table to make sure that your information makes sense, okay, and make sure that you're kind of using the same measurement types in all cases. So notice we have some flower numbers, right, and then we also have how many or how much each of them cost. So if we make a table, we're going to compare the cost to, in this case, the dozens of flowers that I have, because that's how the problem's set up, right? And we know that it costs $11 for 1 dozen. Okay, and notice we have 3 dozen flowers, right? So here's where our unknown goes. Okay, so we multiply by 3, right? And then we have to do the same thing on the top to keep it, quote, proportional. So the answer is just 11 times 3, or 33. Okay, make sure you label what it is, right? We're talking about the cost, so you should say dollars. But let's contrast that with what we know about Part B. Okay, Part B is the cost of 60 flowers. Notice it's not dozens this time. So you either need to change that to dozens, or in my opinion, I think it's better if you just set your chart up a different way. So rather than comparing cost to dozens of flowers, we're just going to compare cost to flowers, or the number of flowers. So the cost is still $11, but how many flowers do you get for $11? You would have to know how many were in a dozen, right? You get 12. And then notice we can line the 60 up here. The X, or the question mark, goes here, right? So if we multiply by 5 here, then we need to do the same here. So the answer is just 11 times 5, or $55. Okay, so last but not least, if we have $77, and notice it asks us for the number of flowers, not the dozens. So we're going to set up our chart to be cost versus flowers. Notice my first column I can just repeat from the last one, right? I know it's going to be 11 and 12. But this time I wasn't given the number of flowers, right? That's what I'm actually trying to find. So $77 is what I have. This is my unknown this time. So to get from 11 to 77, we multiply by 7. So in the end, we get 12 times 7, or 84 flowers. Again, make sure you label what the measurement is, or what the unit is. So what we've really been doing here, although it's not been in fraction form, we've been using this rule. You're allowed to multiply or divide, for that matter, by the same number on both the top and the bottom of a fraction. Okay, we learned that in our fraction unit, right? And hopefully you remember why we're allowed to do that. Okay, if you multiply by 3 over 3, for instance, it's because you're just multiplying by 1, right? And if we multiply something by 1, it doesn't change anything. So it's just like you're multiplying, or in the case of division, just like you're dividing by 1. In both cases, that doesn't change our quantity at all. So before we look at another one, young children especially make this mistake. So as a teacher, you need to know kind of where the common pitfalls are. When I taught high school, I always kind of knew where, especially after I'd been teaching a while, I knew where they were likely to make mistakes, and I could kind of address those before they happened. Okay. So if you have a proportion like this to try to solve for, okay, one of the more common kid mistakes is to remember that they need to do the same thing to both sides, but maybe to try to do this. Add 4 to both, okay? But this is not what we do, right? So I just want to say no so that you don't think later on, hey, she said that we could do this, okay? The reason it doesn't work is because what do you get when you add 4 to the top? You get 5 over 6, okay? And the problem with that is not the same as 1/2. It's not proportional. So it doesn't check out mathematically because we get things that are not the same as each other or not proportional. Okay, so notice the reason this doesn't work is because here we are actually changing the ratio. Okay, we're changing the value of that ratio rather than keeping it the same as long as we reduce it. We're changing the value of the ratio. So even if we reduce it, we're not going to get the same thing back again. Okay, and that is unlike when we multiply by 1 and the value doesn't change. Okay, so let's look at another example. Let's use a proportion to solve. So a proportion is really similar to a table, it's just we don't have the fancy organization of the table. The math involved is really the same. So let's say that we have a committee and there's some sort of bylaw or rule that says the ratio, it must have a ratio of 3 boys to 4 girls. If the committee has 28 total members, how many are girls? So I kind of switched up the information on you. We're comparing boys to girls, but then I'm asking you for a different type of measurement. So let's talk about what we were given. We were given that there were 3 boys for every 4 girls. So notice that this is a part-to-part comparison. Okay, but notice that's not what we were actually asked to use or find. We're asked to compare girls to total members because that's the information we were given, right? We were given 21 total members. 28, I'm sorry. Okay, so we're being asked to change basically from a part-to-part to a part-to-whole comparison. All right, so let's see if we can do that. So let's see if we can set up how many girls there are to total members. So there are 4 girls, right? And then you just need to think about how many total members there are kind of per group, right? 3 boys for every 4 girls, which means there's 7 total. And then notice we can set up the proportion just fine, right? The 28 goes here. The question mark goes here, right? What do we multiply by to get from here to here? We times it by 4, and so we'll do the same here. Okay, so we end up getting 4 times 4, or 16 girls. So make sure you're reading the problem and changing it accordingly. All right, so let's just do a variation of the problem we just did. So use example 3, and let's say there are 20 girls interested in the committee or in being on the committee, but only 6 boys so far. And the question is, how many more boys need to be recruited so that we can keep our desired ratio? In other words, we don't want to turn any of the interested girls down, so we just want to find some more boys, and then all the people who want to participate can. Okay, so this is one of the problems where we have maybe not some extra numbers, but you have to decide what should go in your ratio or proportion. So I know I'm supposed to have 3 boys for every 4 girls. By the way, I can go back to a part-to-part comparison because that's the problem, right? I've set up a part-to-part comparison. I don't even mention how many total members there are, really. I do mention that there are 20 girls. And notice, I'm not going to put the 6 in there, okay? Because of this phrasing so far, indicating that the 6 isn't going to be our final answer for boys, okay? So that doesn't need to go in our proportion at all. We just need to try to figure out what do we need to multiply by. Okay, and of course in this one we're multiplying by 5. So 3 times 5 is 15. Okay, we need 15 boys, but we already have 6. So then of course, how could we figure out how many more we need? We would just subtract, right? So we need 15 minus 6, or 9 more boys. So I see this a lot in the younger grades. You have students that really struggle with word problems, and they just want to try to stick all the numbers in the problem somewhere. And so you always want to give them maybe some higher order thinking questions like this that really test to see, do they actually know what's going on, or are they just inserting the numbers into whatever process you're doing? Because notice in this case, we really didn't use the 6 in our proportion. So that would be a good thing to check, okay, if you're the teacher. All right, so the last thing that I want to look at is the unit pricing worksheet that was in your worksheets to print for the week. So there's some activities that you can do on that worksheet. So really that's nothing that you're going to turn in. We'll just do a couple of examples. But unit pricing can be a really good way to teach students about proportions. So maybe you don't know this, and if not, the next time you go to Walmart and are buying something, the price tag should list the price, but it also usually lists like the price per ounce or the price per pound, depending on what it is. Okay, and that's actually how you're supposed to compare 2 sizes of items to find out if the bigger one is actually the bigger buy or the better buy. Lots of people assume that the bigger one is the better buy because that is most often the case, but I found that's not the case always. Sometimes you can buy 2 smaller containers and actually have a better buy. Okay, so this will be a good practice in finding some rates. Okay, notice these are rates because it's price, which is money, per unit of measurement, right, or volume, and this is volume per money. We're just flipping them around. Okay, so I just wanted to look at kind of these 2 alternative ways to look at it. So if I want the price per ounce, then I'm going to say the price per how many ounces I get, right? And how many ounces do I get? I get 24 ounces. So if I want the price per ounce, then what I'm asking for is how much does 1 ounce cost? So notice, remember I said with proportions we can either multiply or divide. So notice we're dividing by 24. So that's what we'll do here too. Okay, so if you do $2.79 divided by 24, you're going to get about, if you round it to the nearest penny, and you need to, about 0.12 cents per ounce. Okay, notice rates we usually write with that little bar, right? That means per. But ounces per dollar would just be the other way, right? So we would do ounces compared to dollars. And notice the 1 would go with the dollars this time. So even though this is a little stranger, what could we divide $2.79 by that would give us $1? Well, you could just divide by itself, right? That's how you get 1. You divide something by itself. Notice in both cases we would need a calculator, so I wouldn't really say that I think one way is more difficult than the other. But if you do 24 divided by 2.79, you get about 8.60. So make sure you know how to say that. This would be 8.60 ounces per dollar. So as you look at the worksheet that I handed out, just verify kind of which way you're looking. By the way, if you're looking to get the best deal, you would want the least amount of money per ounce, right? So you would want the smallest quantity if you compare them this way. But notice if you compare it this way, you would want the most ounces for your dollar. Okay, so you have to kind of change your mode, right? So here the best buy would be the smallest number, right? The lowest price per ounce. But here the best buy would be the largest ounces per dollar. Okay, so kind of a shift in thought there. If I were teaching this, to be honest, I would probably have my students do it one way. I'm showing you two ways so that you understand that there's kind of that thought process there. All right, so last problem for this lesson. Let's compare a 64-ounce box of detergent that sells for $12.50. And let's compare that to a 32-ounce box for $7. The question that I want you to tell me is, which one is the better buy? Okay, and we're going to do it with both ways. Okay, so we're going to try it with both ways and mention what I talked about in the last example. So method A, we're going to find the ounces per dollar. Okay, and we're going to choose the largest. We want the most ounces for our dollar. Okay, so we would want to choose the largest one if we wanted the better buy. Okay, so let's compare the two. So we've got 64 over 12.50. Okay, so if you were to divide that out, okay, which is all you actually have to do, you get 5.12 ounce per $1. Okay, and let's compare that. That's the big box, right? Let's compare that to the smaller box. So 32 ounces for $7. That doesn't come out nice, but it's 4.57 ounces per dollar. Okay, so notice we want the largest quantity of ounces for our dollar, right? So this is the better buy. Okay, so that's one way to do it. And then the second way to do it is, honestly, when I mentioned finding the unit pricing at Walmart, this is the one that's actually on the price tags at Walmart. So if you've never noticed that, maybe you've not had to bargain shop or something, but I always want to know I'm getting the best deal, just I guess because I'm cheap like that, but frugal, I like to say. Okay, but look next time you're at Walmart. You'll have like a box of cereal that costs $3.59, and then it'll tell you how much per ounce it is. Okay, and you can compare that to other types of cereal or even other cereal of the same type, just different sizes. So for this one, we're going to do $12.50 divided by 64 ounces. Okay, and then notice we want to choose the smallest, right? So this works out to be about 20 cents if we round it. It's actually like 0.1953. Okay, so it's 20 cents-ish per ounce. And let's compare that to the $7 box that contains 32 ounces. And if you compare them, you end up getting right around 22 cents per ounce here. Okay, so if you're the consumer, right, you want to pay less per ounce, right? So this is the better buy. Okay. The point that I'm trying to make here is you can't just give students like a rule that says, oh, just pick the bigger one, because it would actually depend on which way they figured it, and you're going to probably see it both ways. So I would be much more interested in my students understanding that, hey, I want to pay the least amount per ounce, or I want to have the most ounces per dollar.